Cool. So thank you very much for everyone attending this presentation for my PhD, Pathways to Net Zero Energy for Engineered Wood Multi-Story Buildings in Australian Subtropical and Tropical Climates. So today I'll be giving an outline of the research project and its significance, looking at knowledge gaps and research aim, the research objectives and questions, research methodology, current progress, and my research plan. Cool. So the significance of my research is that building construction operations account for 39% of the global energy-related CO2 emissions. Therefore, the building construction sector is widely considered to have the most feasible potential worldwide for reducing greenhouse gas emissions in the short term. Therefore, there's a rapid and far-reaching transitions are required in the building industry. This research is most interested in exploring the use of engineered timber instead of conventional multi-story construction materials in Australia, as globally substituting concrete and steel with wood products where possible is estimated to reduce CO2 emissions between 14 and 31%. And this implies that reducing the operational energy is also a key part of my research. The initial development of modern CLT as a structural building material took place in Austria in the 1990s. And we can see that throughout Europe and globally, CLT production has really increased exponentially. Although it's unlikely that concrete and steel will be completely eliminated from the construction industry, these current trends reveal that engineered wood buildings will play an increasingly important part of a viable solution for multi-storage structures. One Melbourne project that has catalysed interest in Australia is the Forte apartment built in 2012 as the first Australian CLT building. The International House in Sydney is the first engineered wood office building in Australia using both cross-laminated timber and glue-lam timber, and Gillies Hall, which is the background image here, which is a selected pilot project for this research. It's 150 student apartment dormitories located in Melbourne, and the motivation for building with engineered wood in this project was in line with Monash University's net zero carbon emission strategy. The issue is that these were all located in tropical warm or tropical climates, and this research asks if it's appropriate to take these designs generally copied from Europe. There's a very limited number of international tropical climate engineered wood projects that we can draw knowledge from. However, there are some, such as WoodTech, which applies a novel pressure equalized rain screen system to reduce high-risk rain ingress associated with tropical climates. The Singapore Sustainable Academy in tropical Singapore, which is a CLT and glue-lam structure built on top of an existing building, and 25 King Street, which is currently the tallest and largest engineered timber office building in Australia, located in Brisbane. However, King Street only exploits the timber to the internal, and thus is not so relevant for my research. Similarly, there's also limitations for highly energy efficient projects built in tropical climates. Though there are a few that we can kind of gain some insights from, and that's the Austrian embassy building in Jakarta, which uses a very high level of air tightness to prevent exterior moisture from coming into the structure in the building. The Brook building in Human China, which has a 80% reduction on energy use compared to typical projects. And the Star Garments Innovation Center in Sri Lanka, it was able to achieve 50% cooling reduction demand compared to typical tropical monsoon climate buildings by using innovative mechanical systems for enhanced dehumidification. All these projects relied heavily on climate-specific design elements, and though this does show that extremely low energy use is possible in cooling dominated climates. So when we're looking at Australia and towards the future, Australia is one of the most urbanized nations in the world, 90% of its population living in 0.22% of the country's land area. And this graph here shows the distribution of population and shows that there's a massive increase in multi-story buildings that is needed to supply population growth. And on the right-hand side, we have the distribution of climate zones around Australia, where this red climate is the hot and humid climate zone and the focus of my research, where there's extreme temperature and humidity. And it's also worth noting that climate change will bloat these areas and increase the significance of reliable, durable urban buildings. However, the Australian construction industry is currently not well equipped or prepared to build in timber. The ABCB found that Australia was amid an epidemic of mold and dampness, where new buildings were experiencing unacceptable levels of condensation and mold linked to negative impacts on human health and amenity, as well as the building structural integrity. An increased adoption of CLT will lead to increased risks, and this needs to be managed. This is especially the case for highly efficient buildings, highly energy efficient buildings, as if these are designed with incorrect control layers or insufficient ventilation, they have increased risk due to their air tightness levels and often increased use of vapor permeable materials. So the knowledge gaps and barriers for the construction industry in building energy efficient multi-story CLT buildings in subtropical and tropical climates include understanding the hygrothermal behaviour of CLT assemblies, including Australian CLT products, which are yet to be characterised in the Australian context. How to best construct CLT buildings in hot and humid climates, considering other engineering services and moisture management strategies, as well as the performance requirements of engineered wood to achieve net zero energy buildings, and exploring the benefits and issues of engineered wood net zero energy buildings on thermal comfort. And lastly, understanding if economic advantages exist compared to conventional construction methods. So these unknowns need to be solved as opportunities exist alongside risks to develop climate-specific designs for the Australian context. This research fills the knowledge gaps by developing, through both simulation and physical testing, a holistic approach to the design and construction of multi-story net zero energy buildings that employ climate-specific CLT solutions for tropical and subtropical Australian climates. So for objective one of this research is to identify the most energy efficient design and strategies for achieving net zero energy engineered wood buildings in subtropical and tropical climates. And objective two is to understand the hygrothermal behaviour of CLT constructions when utilised in subtropical and tropical climate-based net zero energy buildings. This slide presents the research questions that require answers to meet the objective, while the methods chosen are also displayed to show the relationships with the research questions. Number one is, what are the operational requirements to meet a net zero energy definition for the Australian hot and humid climate? And number two is, what are the life cycle costing of durable net zero energy buildings in comparison to conventional multi-story buildings? For objective three, the first research question is, what are the heat, air and moisture behaviour of CLT products used in Australia, along with their associated constructions, including control layers, engineered wood and adhesive properties in subtropical and tropical climates? Number two is, what are the impacts of construction wetting, driving rain and interior conditions on the durability of engineered wood assemblies in subtropical and tropical climates? What are the most efficient CLT assemblies and junction details and high performance buildings that can dry sufficiently and reduce risk of interstitial and surface moisture accumulation? How to achieve integrated CLT facade performance considering acoustic, thermal, weatherproofing, fire resistance, ventilation, structure, constructability and other durability considerations, and how these considerations influence the hygrothermal performance of the envelope and the building as a whole. The research methods utilize a mixed methodological strategy, where objective one utilizes simulation research, and objective two utilizes experimental research, simulation research, and then lastly, experimental research again for assembly testing. So now I'll go into a brief description of each of the methods used in the methodology. And in the next section, I'll go into where I currently am in my current progress in these methods. On the right, you can see a flowchart for the relationships of the methods, presenting how the outputs of each method becomes input in the next method. For objective 1, this included a literature review of international net zero energy definitions. This assessment looked at Green Star, LEED, Neighbours, Living Building Challenge, and the Passive House Standard, among others. However, only the Passive House Standard included mandatory considerations for occupant comfort and build quality for the project. The Passive House Standard is an ultra-low energy building standard that offers a robust framework for delivering net zero energy buildings. So the next section is the energy simulation section. This is where the pilot project design is simulated in a few different climates in subtropical and tropical Australia. These were selected as Brisbane, Cairns and Darwin, and simulated to achieve the whole building net zero energy building target. This simulation method is designed to set envelope performance values and interior conditions for the pilot project to achieve net zero energy. And then these can be analysed in Objective 2 for the hydrothermal performance. The relevant energy building simulation programs used were the steady state whole building simulation package, the passive house planning package, also the dynamic simulation program, IESVE, and the third program is WFE Plus, which is able to model moisture flows throughout the building elements. And the last segment of Objective 1 is life cycle costing. This phase of the research analyzes the optimized energy simulation models of the CLT pilot project against minimum requirement CLT reference cases. So we can see here, these are the different design options, which will be analysed and compared. This focuses on the life cycle costing to give a greater understanding of the results of this research. So for Objective 2, the next stage is laboratory testing of laboratory material properties. So this determines the hygroic properties of CLT products and adhesive layers, commonly used in Australia using small scale CLT samples. This is used to generate relevant hygroic properties, which are very important input parameters for the hydrothermal analysis. So these includes properties such as the liquid water capillary uptake, moisture storage capacity, and the water vapor diffusion resistance as shown in this image. And currently we're looking at collaborating.
So in the, like where that little chat bar was, there's a little section there.
Sorry, I think someone's speaking. So I'll continue.
Yes, please continue.
Yep, sorry. Yep. So in the next section, this is looking at long-term field monitoring of the CLT building in tropical climate, where it's exposed to high termite risk, rain loads, and relative humidity. Here we're measuring moisture content to calibrate and validate the hydrothermal simulations, where we're inserting moisture content sensors in the walls. And currently this case study is under construction. I'll show you some more progress about where this project is in the next few slides. And then for the hydrothermal risk analysis section, so this method takes the material properties derived from the lab testing, the previous step, and then so kind of feeds them together, and the building and climate parameters and construction details taken from the pilot project, and simulates them using hydrothermal software to understand the risks and explore design options to minimize those risks. So this formulates strategies for the moisture control layers, such as the location and type of membranes. And then for the last step, assembly testing. So this method involves large-scale testing of prototype assemblies during imperfect construction, where there may be cracks or inbuilt moisture, or non-ideal construction, such as rain during the construction, or dust, or the effect of dusts or treatments in the timber. So now going to progress. The research has identified appropriate net zero energy building standards, and as well as a pilot project. We now have some energy results using one of the chosen simulation program. We have some LCA results from Monash University pilot project. We've now procured the sensors and have a monitoring strategy, and are very close to installing these moisture content sensors. And we have some durability simulations using the hydrothermal simulation programs and understanding their risk. So for the pilot project, which is Gillies Hall, so this image was taken during the blower door test. So the use of the passive house provides a rigorous design and construction standard, which is able to provide significant energy savings and offers a robust framework for delivering that net zero energy building. So Monash allowed us to access the data of this pilot project, and then this was subsequently simulated in different climates. So the potential for CLT buildings to achieve this passive house standard has only been minimally investigated in the subtropical and tropical climates. Therefore, this next step looked at how to adapt the design to deal with the high humidity and excessive heat loads. So typically, passive house principles include these 5 different elements. And these are generally for temperate climates. However, in hot, humid climates, the centers more around reducing the cooling and dehumidification demand. And this is achieved through, similarly, through high quality glazing. However, it's more of a focus on reducing the solar heat gain coefficient to reduce the solar gain while maintaining high visual transmittance. Again, also including appropriate ventilation. However, this is more on a focus on energy recovery with recovering that latent energy required for dehumidification. Also, air tightness is incredibly important for cooling dominated climates. However, it was found for thermal bridging effects was not so significant. Instead, external shading was far more important. And thermal insulation was also didn't have the same sensitivity, and external finishing and finishes was more relevant to a passive house and high energy efficient projects in cooling dominated climates. When looking at the energy allowance in the passive house standard, there's an alternative allowance that takes into consideration the dehumidification fraction, the air change rate, and internal moisture loads. So in Cairns and Brisbane, we have an increased latent energy load to dehumidify the air and provide internal comfort. And we can see that it's considerably higher than climates such as Melbourne. So when simulating the pilot project in Brisbane, it found that the research found that there was a number of steps from taking it from the temperate climate CLT passive house. It was still possible to achieve the passive house standard using reducing the internal gains, reducing the SHGC, increasing the surface emissivity and shading, and then implementing an energy recovery unit with humidity recovery. So it was just able to achieve the passive house requirements. However, if we looked at adaptive comfort, where internal temperatures such as 26 degrees in summer, as well as not 60% internal relative humidity was considered as being comfortable, then there was quite a large drop in cooling demand. So when looking at and considering energy efficient buildings in cooling dominated climates, it's definitely possible to achieve a very high efficient building. And this led to a cooling demand reduction of 75%. In Cairns, it was quite similar. And it was similarly able to achieve the passive house standard. And we can see here that the target is far greater than in the previous one. So it was around 25 kilowatt hours per square meter per annum. And for Cairns, that was the target was raised to 61. However, there was also shown a large benefit to seal the windows during the day and prevent humidity from ingressing through ventilation into the building. And while not specifically part of my research, I had a look at the CO2 emissions over a 60-year building timeframe, and which showed that there was significant reduction in greenhouse gas emissions from a reinforced concrete building as usual for the pilot project, of about 58% for embodied materials and 63% reduction for operational. And then for the monitoring project, so this is a 2-story residential project near Cairns. This image here is showing the CLT panels being delivered. So this project is designed for cyclonic winds, high humidity, and termite risks. The sensors have been tested and successfully run, but they've not yet been employed in assembly. They've been installed in the northeast to measure solar-driven inwards diffusion effects and moisture content, which might be observed when the sun shines on damp walls, and to the southwest to measure worst-case conditions due to increased water-driven rain and wind-driven rain and minimal drying potential on moisture content. And a number of interior temperature and humidity sensors will be installed as well. So this is the project as of a few days ago. So we can see that the ground floor CLT panels have been put in. The steel framing structure has been installed, and as I think next week, the first floor will go up as well. So the owner builder, I chatted with him last week, and this ground floor went up within 6 hours. So this shows how quick it was put together. However, unfortunately, during construction, this construction site experienced torrential rains, which potentially will affect the moisture content. Will affect the moisture content. So it'll be interesting to see once we put the sensors in how this project is faring. So the moisture content sensors will be inserted in 3 different depths with a redundancy array of sensors in each orientation as well. And these will measure both at the interior and exterior surface, as well as in the middle of the panel, to understand the transfer of moisture through this assembly. So there was also a delay in construction due to steel manufacturing. And yeah, just zooming in on that, the pin type, just showing how the pin type sensors will be installed. So a building moisture design tool was used to simulate the hygrothermal performance of these assemblies. So WFI was used. And this is the assembly used in the pilot project. And the way that I've simulated is I've added wind-driven rain against the weather tightness membrane, and then an increased interior equilibrium moisture content of the materials. I just realized that I'm already at 25 minutes and I've still got a few more slides to go, so I'll try and run through a little bit faster. But yeah, so these simulating it with the wind-driven rain and increased moisture content is as per ASHRAE 160. And when we simulate it, we're able to see certain layers and how that affects the moisture content. So here we can see, this is the moisture content here, how slowly it dries out on that exterior slither of CLT. So this is where the risk is occurring on this outer surface. So within even 6 months, when modeled like this, when there has been rain during construction, there's still quite a high elevated risk due to moisture on that exterior surface. When looking at some design options for Brisbane, so I'll just explain this graph where 3 mold growth, this is modeling mold growth index. So mold growth index over 3 typically corresponds to over 3 is something that's a decay cycle, which is not adequate. However, something under 3 shows us that there's mold growth that can only be seen under a microscope. So that's, and it drops back off. So the decay cycle is not exponentially increasing. So here we can see that when modeling wind-driven rain and increased exterior moisture content, Brisbane can be the project. Sorry, it's quite okay to construct a project with permeable insulation. However, impermeable insulation such as EPS or XPS has an increased risk. But then when we look at increased permeable membrane to increase drying or increased air changes, there is a decreased risk to these design choices. And then notably, if we don't include any moisture content, as in it's a dry construction, then there's very little to no risk at all. And then when we model driving rain inside of the membrane instead of on the membrane, this also shows risk for permeable insulation as well. So then we really need to look at increasing the air changes to get reduced risk and something that could be considered an appropriate assembly. So for cans, cans shows that it's very difficult to achieve a appropriate assembly almost at all. Therefore, we have to look at dry construction with correctly sealed membranes. So when it is dry and there is correctly sealed membranes, then we have a mold growth index that is appropriately low. So the mold growth index does stay below 3. However, this needs to be modeled over a 10-year cycle. So this does give me a little bit of concern for my monitoring project. So the owner may have to put in drying fans to ensure that that CLT does dry and return to a safe moisture content level. Cool. So what's next? So I still need to do dynamic and transient whole building simulations to understand if there is effects due to the CLT, as it is vapor permeable. Vapor is able to move through the CLT, even if it is quite slowly, and understanding if this affects the energy performance. I need to complete the field monitoring, complete life cycle costing, and the simulation, the hydrothermal simulations, looking at different interior conditions, different membranes and different insulation, and different exterior, looking at different weather files and different climate zones as well. So that's where I am for objective 1. And then for objective 2, looking at material and assembly testing and potentially having some collaboration with the Department of Agriculture and Forestry. And then my research plan is, I'll just go through this fairly quickly. Yeah, not really too much to say, but due to COVID, this has kind of pushed everything out by about 6 months. And so currently working more on the simulation results, and the assembly and material testing will be pushed to the start of next year. And then the thesis structure. And then for conference activities, last year gave a presentation at Pacific Timber Engineering Conference, a publication and presentation in China at the International Passive House Conference, and an abstract has been accepted for the South Pacific Passive House Conference, and I'm waiting to hear back from the World Timber Engineering Conference, which is pending due to COVID. And then some collaborating organizations around some of the work I'll be doing in the future around the those future research sections. Sorry, thanks guys. I just noticed that I was just trying to speed up at the end, as I noticed I was going over 30 minutes. Thank you very much. So please let me know if you have any questions.